In this video, we're going to look at question 6 from page 21 of the course notes. What I've done here, because I've covered some of this already, is I've started with some of the working. We'll actually explain before we move on to the diagrams, but I'll explain how we got the values that are on your screen just now. So we started off at the top, just indicate this with a little green dot start up here. This is the sum of all of our shear forces. So we know that we have VA and VB. They're our support points in our beam. So they're going to be our upward forces reacting to the downward loads applied. And that there's 3 downward loads we need to consider. So this was a little bit different with this question is that we have different values for the uniformly distributed load in different sections of beam, but we'll highlight where each force comes in. So this 20 kilonewton force here, that's what's been applied, what I've marked as point C. This 12 times 5, well, where did this come from? Well, 12 is the UDL on our left-hand side of the beam, and it covers 5 meters of beam. So that's where 12 times 5 comes from. And lastly, we have the UDL on the right-hand side, and against 15 is the UDL value. I've underlined both in red, and it covers 2 meters of beam. So it's going to be 15 times 2. That's how much the value of force downwards due to that portion of UDL in the beam is. So we have to be a little bit more careful with our calculations here, but at the same time, it's just using UDL over a portion of beam like we've done before. So we deal with it in 2 separate sections, but that's how we get these values. And when we rearrange, we get what we've got on the line below, which is VA plus VB is equal to 110 kilonewtons. So the total upward force must balance out the total downward force due to that point force at C and those 2 UDLs. So I'll remove these markings just now to tidy our diagram and equations up for the next part of the question. So we're in a similar position as we have been in other problems like this, where we know the total value of the 2 upward forces, but we don't know what either one is. Well, as before, we consider taking the moment at one of the points where those forces apply, so we can get an equation that uses the other force. So in this case, if we take the sum of all the moments at point A, which we know adds to 0, we can find a sum involving the value VB, the force at point B. That's exactly what we've done in the second equation that's on your screen here, which I'll indicate again. The green dot shows what I'm talking about just now. And I've considered point A and thought about all the forces and the moments that they cause relative to point A. So hopefully the first point I've considered 20 times 5 is what you'd expect. This is the force acting at point C, and it acts at a distance of 5 meters away from point A. So it's 20 times 5. The next thing to consider is the UDL on the left-hand side of the beam. So when we've got 2 separate UDLs, we consider them separately. So we consider a 5-meter section of beam from A to B. So this is 5 meters here. 12 kilonewtons per meter is the UDL. And the 2.5 meters, well, it applies halfway between A and C. And that is also 2.5 meters from A. You'll see why I'm making this extra clear in a second, but halfway between A and C is 2.5 meters, so that's where we get the 2.5 here. Now, where I need to think a little bit more carefully is for the force causing the moment and the right-hand side UDL relative to A. So, as we'd expect, it's going to apply halfway between the UDL, between C and B. That's where this is applying. And this is 1 meter away from C. But of course, C itself is 5 meters away from A. So we're considering the whole distance from A to this point halfway between C and B. So this is 6 meters we're going to be working with here. So the point force we're going to use to approximate this UDL does apply halfway along the UDL between C and B. By that point, this 1 meter from C is 6 meters from A, as I've shown in red there. So what we've got here is the 15 kilonewtons per meter. It's a 2 meter section of beam, but the point is 6 meters away from A. So that's why that's a 6 there, not a 1. We'd be expecting if it was just a standard beam and it was halfway along the 1 meter, but it's not how far along the UDL it is how far is that point halfway along the UDL from point A. And we're left, as you'd expect at the end, with minus VB times 7. VB is acting in a counterclockwise direction, and the total length of the beam is 7 meters from A to B. So if we put all of these in, we can add 7 VB across, and we add all those other numbers up, and we get 7 VB is equal to 480. So dividing that through by 7, we get VB is equal to 61.43. And using that relationship we established at the start, we can find VA. So VA plus VB is equal to 110, subtract 61.43, and we're left with 48.57 kilonewtons. So because we've done some problems like this before, I've tried to speed it up for this video so that we can spend a bit more time again looking at the shear force and bending moment diagrams. So if you want to have a look at that just now, is a good time to pause and have a think about this before I move on to doing the shear force diagram. So let's do that then. Let's look at the shear force diagram. So I'll clean up our whiteboard a bit, rub all of this out. I'll quickly do my best. I want to write on the value for our forces because we'll need those. So VB was 61.43 and VA was 48.57. So I'll write them on. We definitely need these for what we're doing next, our shear force diagram. I'll leave those markings on, they might be useful. So shear force diagram, let's draw a line for that. This is our shear force. This is our zero line from our shear force diagram. So mark all of our shear forces on here. So this is 0, 0 all the way along this line. So we do exactly what we did in question 4 and other questions like it. We move from left to right. Starting on the left-hand side, we've got a force being applied, force at VA, 48.57 kilonewtons, and we'll mark this in our diagram here. And we just draw a line straight up from the start of our line to this point at VA. So that's our first point. And I'll mark on here 48.57. And we use the same process that we've done before to work out the forces just left and just right of each point. So the next point we want to consider where a point force is applied that's not a UDL is point C. So let's think about C. So at C, we've got, we'll do it over here, we'll do it on the diagram. At C, so this is the, we've got just to the left of C, what do we have? So we have an upwards force of 48.57 due to the force at A, and we've got a downwards force due to the UDL. So at point C, we've got this UDL to the left, it's 12 kilonewtons per meter, over 5 meters of beam, and it's 2.5 meters. I'll do this in black so you can see it's because it's not the same point we're talking about. It's 2.5 meters here away from C. So that means nothing. That's the moment I'm thinking about. Is shear force we're talking about here. We don't need to consider the distance right now. So forget I just said that last bit. It's a total of 12 times 5. It's the force. We're not interested in where it's applied, we're interested in the total force. So just to the left, it's 48.57 minus 12 times 5. So put this into our calculators. It's just force we're considering here. 48.57 minus 60. And that is going to give us 11.4. And you maybe even see why. You might even think like me sometimes. You start thinking, oh, I need to work out the distance here. The distance away from the point only matters when we're looking at our bending moment or our moment calculation. We're considering force, we're just interested in total force being applied. So in that section of beam on the left-hand side, it's 12 kilonewtons per metre, and there's 5 metres of beam to the left of the C, and that's all we're interested in. At this point where the force applies is not what we're concerned with. Just to the right of C then, we've got exactly those same two forces, the 48.57 minus the 12 times 5. And then we've got the force being applied at C itself. That's minus a further 20. And you can probably see that 11.43 minus a further 20 is going to be minus 31.43 kilonewtons. So we can mark these on our diagram as well. So this is roughly where C is in the beam, just for, so we'll call this here, this is our point at 11.43. This is our point at minus 31.43. Now write those numbers on the diagram as well. And again, we draw these as a vertical line between two of them because they're at the same point in the, try that again. They're at the same point in the diagram, so it's just a pen was playing up there. Same point diagram. So we draw a vertical line between the two of them. And because it was a UDL, we draw a straight line, but an angle coming down from 48.57 down to minus 11.43, because that's the first point just left of C. Then we want to consider point B, what's happening there, because that's our next point force. So at B, just to the left of B, we have 48.57 up the point A. We've got a force down due to the UDL on the left-hand side, minus 12 times 5. We've got the force at C downwards, minus 20. And then we've got the UDL on the right-hand side down. So that's minus 15 kilonewtons per metre times the 2 metres of beam that happen to the, on our beam that's to the left of B. And nothing else, because we're not going to consider VB at this point, because we haven't got that point in our beam. So if we add all of these up, what we get is minus 61.43, which you might have been expecting again, because that's what VB is equal to. So we'll mark this in our diagram here. Roughly here will do. So that's minus 61.43. I'll have a line coming down, a straight line coming down to this point. Well, I'll give it one more go. That's a bit better. And then what's just right of B? So we consider all those forces that are just left, 48.57, that's the force at A, minus 12 times 5, the UDL on the left of the beam, minus 20, the force down at C, minus 15 times 12, the UDL on the right-hand side of the beam, and then we add on 61.43, because that's the force we worked out in the first part that's acting at B. So this is going to all add up to 0, as we'd expect. Because we expect to have 0 at either end of our shear force diagram, and that's what we do have. So draw a straight line there. And that completes our shear force diagram. And it also gives us a little bit more information we're going to need for the bending moment diagram in a second. We know that point C is here, because that's what we worked out. So that means the point at which we cross the shear force line, where shear force is 0, is going to be somewhere between A and C. And we'll need that in a second to find out maximum bending moment. So again, pause if you want to review these calculations, and I'll move on to the bending moment diagram. Just moving our diagrams up a little bit, make a little bit more space there. So the bending moment diagram, well, as before, things to think about are what are the bending moments at points A, B, and C. Now, because of the type of problem this is, the bending moment at A is 0 kilonewton meters, and the bending moment at B is 0 kilonewton meters as well. And There's other examples of why this is the case at B, but what happens when we add all our moments up? Because it's not a cantilever beam, because it's not got a fixed support there at B, there's no moment being supplied at B, so the bending moment is 0. It has to balance out. So the only bending moment we can really calculate is the bending moment at C, which we'll do just now. So MC, bending moment at C. Well, let's just tidy up our diagram a bit so we can have a think about it. So I'll rub all of these out. Let's do our bending moment and think about what's going on here. So for a bending moment, what we do is, I should say point C is that point in the middle. We take a section through the point. I think what is happening to the left of this point. So we won't need to think about the UDL on the right hand side of the beam. We won't need to think about the 20 kilonewton force at C. What's happening to the left of C? So forces acting up the way to the left of C have a clockwise effect, and so are considered positive here. Forces acting down the way have a counterclockwise effect, and so are considered negative. So what's to the very left of C? We've got a force acting up the way, the force A, 48.57, and that's a distance of 5 meters away. And then we've got the UDL acting down the way. So it's 12 kilonewtons per meter over 5 meters. And again, we consider this to be acting halfway along the UDL. And that is also, we need to be clear in questions like this, halfway between A and C. So that's a 2.5 meter distance from C. So I'll draw that in there. 2.5 meters away from C, 2.5. So it's 12 times 5, that's the total force. And it's 2.5 meters away from C. So we can work out the bending moment there. And that works out. So I've got my calculations right, and I think I have 92.85 kilonewtons. So I'll quickly draw in what we've got so far in our bending moment diagram. A wee bit of room over here. So that's our 0 line. MA and MB, which if you question about why they're 0 again, look at the other examples, but if you're just not sure, do ask me. And we'll have a point at C, roughly, that C's about here, that's going to be 92.85. But we know there's a point that's bigger than C, because that's where our shear force is 0. That's what I've highlighted on the shear force diagram, that red dotted line. I'll put on a wee bit in blue here. This is distance, we call it distance X away from A. So that's somewhere over that 5 meter section of UDL between A and C. Somewhere along that point before we get to C is the point where the total shear force is 0. So what I'll do just is I'll rub out these moments here, read the space, and think, where does shear force equal 0? Well, before we get to C, there's only 2 things that can influence shear force. So, what we want to say is shear force equal to 0. When that point comes, what we've got is we have a force acting up the way of 48.57, and then it's all that 12 kilonewton per meter UDL until we get to C. Now we know if we go 5 meters, we've gone too far. So it's minus acting down the way 12 times some value that's less than 5. So we'll call this X just now till we work it out. So what is X? What is this distance we go from A to C where it balances out, where we have exactly 0 shear force? Well, we can work this out. We say 12X is equal to 48.57. So X is equal to 4.05 meters. So 4.05 meters. So that distance X, that point before C, is 4.05 meters across. So we need to work out what is the what's the bending moment at that point at 4.05 meters. So let's tidy up our diagram again. So we're not interested in the bending moment at C. We're interested at a point here, which will. So that's our 4.05 meters, and that's where we're interested in our bending moment. So bending moment through this point on the diagram here. And how do we work that out? Well, we do it like any other one. So M, and I'll call it M 4.05, is equal to all the moments acting to the left of that dashed red line I put in. So at the left-hand side, we'll have our 48.57 kilonewton force. And because, of course, we're measuring from that point, that's 4.05 meters away from the line we've drawn. And then the moment acting in the counterclockwise direction is going to be due to the UDL of 12 kilonewtons per meter. So as before, it's minus is 12. We get the total force from the distance we're considering. So this is just over the 4.05 meters. And then we consider this to be acting halfway along that 4.05 meters. So that's times 2.025. So just indicate that in green. Effectively, we're saying is the UDL force relative to this point X is here, and that is a distance of 2.025. So it's worth going through this step by step and thinking, am I sure where all these numbers are coming from? But this, the 4.05 came from where the shear force was 0, and then we just treat it like any other point along the beam, so that when we're calculating a UDL, it's the whole length we're considering, the 4.05, and we're considering that applying halfway along that distance. So we put these values in here, and I'll just, again, check that we're getting this right. And that gives us 98.29 kilonewton meters. As a quick common sense check straight away, we should see that it is in fact bigger than we worked out at C. We knew it would have to be bigger than that because that's meant to be our maximum bending moment. If we mark it on our diagram here, you can see down at the bottom of the screen, that's 98.29, and we can draw our bending moment curve. And again, it's not going to be straight lines. We're working with a nice curved line. I'm trying the best I can. It has to peak at the bottom point, come through that point we worked out for C, and that's what gives us our bending moment diagram. So that's another example. So as before, any questions about specific points of that, please get in touch.